Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at the mathematics of running an infinite hotel. This came from a question from one of the regular viewers who was asking about this sort of area. So it's fun when people do that. It makes the whole thing more fun and kind of community. So we run an infinite hotel. So the rooms in this hotel are numbered 1, 2, 3, 4, 5, 6, 7, 8 off to infinity. We are full. Every room is full. Somebody turns up looking for a room. What do? Well, the answer is that we put the person in room 1 in room 2, person in room 2 in room 3, person in room 3 in room 4, so on. We move them all up 1, which leaves room 1 free, so our new visitor can live in room 1. Okay, here's a bigger problem. A bus turns up with an infinite number of people, and they've got t-shirts on that go 1, 2, 3, 4, 5, 6, etc. Where do we put them? Okay, big problem, big solution. The person in room 1 goes to room 2, person in room 2 goes to room 4, room 3 goes to room 6, the person in room n goes to room 2n. So everybody's in an even number, so we've got the odd numbered rooms free, 1, 3, 5, 7, 9, 11. And all this lot, the new lot, they go in those odd numbered rooms. And it fits perfectly, so we can accommodate an infinite number of new guests. It's quite hard to understand infinity intuitively because in the real world, in the world we're used to, everything's finite, right? What about if an infinite number of buses turn up? Each bus has an infinite number of people in. Well, what you do is this. If the hotel's already full, you put the existing guests into the rooms that are indexed 2 to the power 1, 2 to the 2, 2 to the 3, 2 to the 4. So it's basically 2, 4, 8, 16, 32, 64, 1 to 8. You put the existing guests in there, and then the next lot, which is the first bus, they go into the powers of 3. 3, 9, 27, 821, 243, etc. The next lot go into the powers of 5. 5, 25, 125, 625. 3125, I believe, is the next power of 5. And then after that, you put the next lot in the powers of 7. 7, 49. What's 49 times 7? Is it 343? He says, kind of slightly guessing. That's right, isn't it? It's 343. So you put those in there, and then after that, it's the powers of 11. So every number has a unique prime factorization, so there will not be two people in the same numbered room, and actually we have a lot of rooms left over, as it happens. So we can accommodate an infinite number of buses with an infinite number of people. But here's an impossible problem. If a bus arrives with people who have real numbers on their t-shirts in the range from 0 to 100. So there's one with 0, there's one with 1, there's one with 2, pi, which is the ratio of the circumference to the diameter of a circle, e, square root of 2, square root of 3. So the last four are all infinite decimals. You cannot get this lot into the hotel. There is no way. There's just too many of them, even if it starts off empty. And here's why. Imagine you could. So imagine you had the person 0.0000 infinite decimal in room 1, 1.0000, and then you had the person with a t-shirt with pi on it in room 4, E is room 5, root 2 in room 6, and this in root 7. And you just, root 3 in room 7. And they're all in a room. Then here's the issue. If we look at the highlighted numbers, what we're going to do is create a new number, and the person with this number will not have a room. So we're going to take all of these highlighted numbers and add 1. So 0 goes to 1, 0 goes to 1, 0 goes to 1, 1 goes to 2, 2 goes to 3. And so we're going to create a new number made up of those numbers. So it goes 1.1123221. Now this number differs from all the other numbers. It differs from the first number in this place. It differs from this number in the first decimal place. It differs from this number in the second decimal place, and this one in the third decimal place. So this is different to all of these numbers, which means that this person with this t-shirt never got a room. So however you try to put everyone, you'll always have people left over. In fact, a lot of people left over. In fact, you'll have more people left over than you've got in rooms. Almost everyone will be left over as it happens. This is called the Cantor diagonal argument. So what we've done is we've shown that one person will be left over, but in reality, actually, almost everyone will be left over. because the number of real numbers is a lot bigger than the number of integers. Now, we've used the real numbers from 0 to 100. Actually, that's the same as the total number of real numbers. And if there's a lot of clever people watch these videos, if someone would like to put the proof of that in the comments, then we'll give them a shout out in a future video. But so this is a really exciting result, right? And since we're dealing with impossible questions, here's another impossible question. Is there a bus with fewer people than the last one that can still not be fitted into the hotel? And this problem is actually called the continuum hypothesis, because it's the hypothesis that there is no infinity that's greater than the counting numbers but less than the real numbers. And so Cantor came up with the continuum hypothesis. In 1940, Kurt Gödel showed that the continuum hypothesis cannot be proved untrue from ZF set theory. It cannot be proved false. And in 1963, Cohen showed that it cannot be proved true, which leaves us with something of a dilemma. So you've got some choices here. You can either say, well, it's a matter of, we choose the set theory we want. But Gödel was a realist about set theory, so Gödel believed that sets were real. And so we had to have an intuition for what the answer was. We could see what the answer was. But this asks a lot of philosophical questions, because having mathematical theorems that cannot be proved true or false is challenging and interesting and leads to lots of interesting philosophical thinking. I mean, this stuff is really like postgraduate stuff. The early stuff I'd expect a first-year university student to be able to do, but this stuff's really hard. I hope you liked this video. I liked making it. You're very welcome to subscribe and hit the notification bell. I'd love to hear your ideas, more ideas, and I hope you enjoy your mathematics most of all.